Good morning, everyone. I'm Songori from Kasi. Today, I'm so pleased that I could invite Dr. Luca Naticchioni from INF in Rome to our Kasi meeting. He has been doing many important roles for Virgo and Kagra gravitational wave detectors, mainly for development of the test mass payload, which is the key optics of the gravitational wave detectors, and also for low frequency noise mitigation and quantum noise reduction technologies. And now he is one of the most active members for Einstein telescope project, which is the most promising next generation detector. And he is chairing and co-chairing in 4 different committees and divisions of Einstein telescope for Instrument Science Board, Site Preparation Board, and Services and Standard Board. And particularly, he is leading scientific evaluation efforts for the site selection of ET, which will be the most critical decision for this project in a couple of years. So I think this is very good opportunity for us to learn about the current status of Einstein telescope and what we can do with this amazing instrument in the future. So please welcome the speaker.
Thank you, Sung-ho, for your introduction, and good morning to all. I will talk indeed about the Einstein telescope, the new third generation gravitational wave observatory that we are planning in Europe. So this is the summary of my talk, and this is the spectrum of gravitational waves. So we can see all the expected sources, that astrophysical sources that can emit gravitational waves, and all the possible ways that we have to detect them directly or indirectly. And in particular, with ground-based detectors, like Einstein telescope will be, we are interested in this part of the spectrum from few hertz to kilohertz, where we expect to have coalescences of binary black holes and neutron stars, as we already observed with Virgo and LIGO, but also other sources like isolated neutron stars or maybe also supernovae. So this is the current network of second generation of gravitational wave detectors. We have the 2 interferometers of LIGO in US, Hanford and Livingston. Then we have Virgo in Italy and Kagra in Japan. And this is the expected timeline that we have in front of us for the observation runs. We are currently running the O4B observation run. It started indeed a few days ago. And if you see, we have in future planned other observation runs. What is interesting is that after 2035, we will be, there will be also the third generation of gravitational wave observatories. So Einstein telescope in Europe and Cosmic Explorer in US. So at a certain point, we will have the second generation network of observatories in parallel, in coincidence, observation with the third generation gravitational wave detectors. So where we are with the advanced detectors, here you can see with the blue curve in terms of the redshift of the horizon that we can observe. In this case, for advanced LIGO, we are here. And you can see that we are in the local universe, still in the local universe. And this here we have also some of the sources that we already observed. And then if you compare where we can arrive with ET, improving the sensitivity of a factor 10, you can see the green curve in this case. You can see that we are going to the primordial universe, to high redshift, and we will go through the peak of star formation rate to the peak of the binary black hole mergers. And also, maybe we will be able also to observe binary black holes formed from population tree stars. And maybe if they exist also from primordial black holes. So you can understand that it's a big step forward for our observation with third generation detectors. This is indeed what we already observed with the LIGO and Virgo in their first 3 observation runs. So this is the GWTC3 catalog, 90 events. We are not accounting for the new events that we are observing with the 4th observation run, but you still already see that we fill at the mass gap, we are observing even intermediate mass black hole. So it's very interesting. This is one of the big results that we already had with second generation detectors. But we are still here in the local universe. We can arrive to redshift 2 maybe, and then to arrive to the dark ages of the universe, we will need the third generation, so also Einstein telescope. And this is where we want to arrive with this kind of detectors. So this is the scientific case for ET in a nutshell, let's say. And you can see there are many topics in astrophysics, of course, properties of black holes, neutron stars, multi-band and multi-messenger astronomy, which is really important, and also detection of new astrophysical sources that we still didn't have observed, like supernovae and isolated neutron stars. But then there are also important topics in fundamental physics and cosmology, for example, studying the nature of these compact objects like neutron stars, but also testing the general relativity, also having some hints about dark matter, aiming for exotic axion clouds around binary black holes, for example, and then also having some hints about dark energy on a cosmological scale, and maybe also observing the background of stochastic background of cosmological origin. And indeed, with ET, we will be able to observe the entire universe, and we will be able to detect all the binary black holes coalescing back to the dark ages. But to give you an idea of the numbers that we are dealing with, looking to binary neutron star mergers, in 1 year of observation, we expect hundreds of thousands of events. It's a huge number. So you can understand how important it was observing just one kilonova, GW 170817. Imagine to have every year hundreds of thousands of events. It's really impressive. And indeed, you can see in these two plots here, the expected detection compared to the expected population in terms of redshift for binary black holes and binary neutron stars. You can see that in practice, we will be able to observe the evolution of this kind of objects through the entire history of the universe. And also, it is important the opportunity to test the general relativity in strong field regime, which is accessible only through the observation of gravitational waves. And then we also hope to have some indications about the formation of the supermassive black holes that we observe in the center of many galaxies. Indeed, we will aiming to this mass gap of intermediate mass black holes, where we can find the seeds of the formation of these objects. And then, of course, from the merging of binary neutron stars, we will be able to better constraints and study the structure, the internal structure of neutron star, in practice describing their equation of state. And indeed, the neutron stars are for us also an extreme laboratory for nuclear physics. Indeed, you can reach with these objects densities and energies which are not accessible on Earth on high energy physics laboratory. So having thousands of these events is also a source of many information for nuclear physics, for fundamental physics. And let me mention, of course, the power of the multi-messenger astronomy. We already cited this event, which was really important, marking the birth of the multi-messenger astronomy. We observed with the LIGO and Virgo the direction of the arrival of these gravitational waves produced by this object. And then we also had the observation in coincidence of the gamma ray burst, and then the follow-up of the optical counterpart with all the beautiful science that we were able to do with this observation. For example, we explained the formation of the lanthanides through hard processes in these coalescences of binary neutron stars that now we know that are also have this kilonova counterpart. So really amazing. And then we have also another way to constrain the Hubble constant. Indeed, we can use the coalescence of compact objects as standard candles, but we should say standard sealants in the case of gravitational waves for this analogy with the sound, with waves of sound. So yeah, it's really a lot of science that we can do. So let's have a look to ET in particular. ET is indeed a third generation gravitational wave observatory. When we say third generation, what we are meaning is that we want an infrastructure that must be operative for at least 50 years. And we want to have an increase of the sensitivity of a factor 10 with respect to the current generation detectors. And then when we define it an observatory, what we mean is that it will be a broadband detector capable of observation, in particular extending the observation band towards the low frequency below 10 Hertz. And obviously, it must be able to localize the sources in the sky, to disentangle the polarization of the incoming waves, and also to have a good duty cycle for the observation. But ET will be not alone. We know now that there will be also Cosmic Explorer in US. In this case, it will be a different shape if you compare with the previous one, which is the baseline of a triangle. In this case, it's similar to what we have in LIGO and Virgo, L shape, with 40 kilometers and 20 kilometers long arms. So it will form, together with ET, a third generation network of gravitational wave observatories. So ET was designed firstly in 2011 with this conceptual design study. Then we had in 2020 a design report update that we made for the application to the European Science Forum for Research Infrastructures. And we were approved as a project in the roadmap of ESFRI. And yeah, this is what followed the formation, the official formation of the ET collaboration in 2022, starting from more than 1,000 members. And then this is the timeline as we presented to ESFRI. So some of these activities are going maybe longer than expected. For example, the site qualification, also the cost evaluation, but the site decision is here somewhere before 2026. And we are currently here, in particular, we are working on the project breakdown structure, which is an important task, describing all the detectors that will be in the research infrastructure. And it's the first step towards the technical design report that we are preparing. The total budget of ET will be somewhere around 2 billion euro, and only the infrastructure that will be an underground infrastructure will cost something around 930 million. This is a map representing all the institutions that are in our 88 research units. We are currently more than 1,600 members in the collaboration. And if you look in the map, there is also a research unit from Korea. Sung-ho is the team leader of this research unit. So even from Korea, we have collaborators to this wonderful project. And this is a simplified scheme of the ET organization. So we have what will be the future legal entity, the ET Observatory, like the government of the collaboration. Then we have two projects which are indeed really important. InfraDev was meant for the implementation of the research infrastructure to build the observatory. And then we have also a dedicated project for the vacuum system, which is indeed the second more important voice of cost in the project. And then we have the scientific collaboration here with spokesperson, collaboration board, executive board, service and standard boards. And then we have the scientific specific boards. So we have the instrument science board, the computing board, the observational science board, and the site preparation board. This is a more complicated structure, just to give you an idea of how all these bodies works together. It's quite complicated. I don't want to comment it, but strangely, it works somehow. So this is the scientific part. So we have the science boards here, and you can see that each board is divided into several divisions, and all of these divisions are in turn divided into several work packages. So we have many of them, you can see. It's a complex project indeed. So let's see some key elements of ET. ET in its original baseline is a triangular infrastructure with 10 kilometers long arms. And inside this triangular infrastructure, there are 3 detectors, you can see with different colors. And these 3 detectors are xylophone detectors. That means that each detector is composed of 2 interferometers, one for the low frequencies, which is also a cryogenic detector, and the other one for the high frequencies. And this idea was born more than 10 years ago, because at that time, ET was the only proposal that we had for the 3G detector, in particular for the 3G observatory. What we wanted at that time was to be able to localize the sources in the sky. For this reason, we have this kind of design, which is different from what we have currently in LIGO and Virgo. And then it will be underground, as I said. It will be, let's say, 200, 300 meters underground. And there are many enabling technologies that are required for this project. For the low frequency, we need, for example, big substrates for our mirror that are also the test masses of the gravitational wave detector, that will be made in silicon or sapphire, because we want to cool down these mirrors, and we want to have good optical properties and good conductivity, thermal conductivity at low temperature. And then we have also the need for new coatings. We will have to switch the wavelength that we will use for these low frequency detectors, and then also a better seismic filter at low frequency, which is fundamental. And then we have also to mitigate the quantum noise with frequency-dependent squeezing. For the high-frequency detector, indeed, we will deal with high-power laser, and we need to have a stable high-power laser. Then also in this case, large test masses, in this case made of fused silica, as the ones that we are using currently in Virgo and LIGO. But again, new coatings with the low thermal noise, which is challenging. And then a thermal compensation system, because we will inject a lot of power, more power into the interferometers. And then again, we have to mitigate the quantum noise, so with frequency-dependent squeezing. But the big challenge, from my point of view, for ET, one of the biggest, is the low frequency. When we talk about low frequency in ET, usually we refer to this part of the spectrum, below 10 Hertz, below 20 Hertz, let's say. And I told you that with ET, we want to have an increase of a factor 10 with respect to Virgo and LIGO in sensitivity. But if you look here, 10 is here. But then at low frequency, we want to increase the sensitivity of a factor 10 to the 5, 10 to the 6. It's a huge, dramatic upgrade. And it will be really, really challenging. Also because we know already with Virgo and LIGO how difficult it is to improve the sensitivity, to reduce the noise in the low frequency region. And for sure, we have to start from a low noise site. This is mandatory. And then we will need also to apply active noise mitigation strategies to mitigate all the, in particular, environmental noises that are acting in this part of the spectrum. And we have also, I added this point, to learn the lesson from the second generation, because we learn a lesson from dealing with the low frequency noise. So also from the engineering point of view, there are some important key points. We will have to excavate 30 kilometers of tunnels, and we have to deal in particular with groundwater. We know that is really difficult. We have the experience of Kagura, that is an underground detector, and also I have to manage the amount of groundwater that is flowing in the underground infrastructure. We have to excavate large caverns, the larger caverns ever made underground. And these caverns, also the tunnels, must be stable for more than 50 years. This is another challenging point from the engineering point of view. And we need not only structural stability, but also thermal stability, cleanliness, ventilations. But ventilation underground means also noise, but we want to avoid acoustic noise inside our detector. So you understand that it's not easy to find a trade-off designing such a detector. And then I told you that the initial baseline for ET was a triangle. And now we are also considering another option, since as I told you, we will have also Cosmic Explorer as a third generation detector. We are considering the possibility to have two hells. So the standard design that we already use for Virgo and LIGO, also for ET, that means not only one site, but two sites to build ET. And in particular, as a scientific collaboration, we are studying these two configurations in order to maximize the science return and to reduce the risk that we can have with such a complex detector. So indeed, since 2011, when the first conceptual design study was prepared, the situation drastically changed. In particular, we had the first detections of gravitational waves. So we were able to prepare the first catalog of events. We reviewed the populations. The science case was greatly improved. And also we had a huge know-how with the advanced detector. In particular, we know how difficult it is to commission and to make these complex detectors work to reach the target sensitivity. It's something that we learned with advanced detectors. And then the international scenario changed. We have Cosmic Explorer in US. And also, let me say that currently for ET, we have two candidate sites and are both strongly supported by the hosting nations. And we will see it in the last part of the presentation. We have also a potential third site that is still not official, but is there. So we are analyzing these two configurations, having one triangle or having a two hell-shaped detector. So from the point of view of the science case, there was appointed a dedicated committee to analyze all the possible configurations with different shape, with different length of the arms, in terms of how many sources we can detect, which resolution, with which precision, sensitivity, and so on. And it resulted in an impressive work that was published. This link, you can find it. There are almost 200 pages. It's really a beautiful work. I cannot show you all the results because it will require an entire session, but I just give you an idea with a couple of tables. Here we see, for example, what we expect for binary neutron stars mergers in 1 year of observation. There are many interesting points in this work because here you can see how many sources we can observe with a given signal to noise ratio. And if you see here, if we have a triangle with 10 kilometers long arms, in which all the interferometers are working together, so 6 interferometers, 3 of them cryogenic, that are working, for example, let's see this number, and then let's see what happens if we have 2 hells with 15 kilometers long arms, but misaligned by an angle of 45 degrees, more or less, in which they are operating only the high frequency detector, so only 2 interferometers versus 6 interferometers in the same location, and we have a number which is similar. So it's already here you can see that there are advantages in having 2 hells instead of a triangle, of increasing the results that we can achieve with ET. But nevertheless, even with the triangle, you can see what is the improvement from LIGO, Virgo, and Kagra in 05. So with an improved sensitivity that we expect with the next observation run, we go from 250 to over 100,000. So yeah, it's already a big step forward with the triangle, but then we can further increase the situation with the two hells. And there we can see the same thing, considering, for example, the resolution in terms of luminosity distance or capability to localize the source in the sky, which is for a binary neutron star is important to give the information to the electromagnetic observatories worldwide. So this is an important parameter. You can still see here that two hells are performing in a good way. And it is interesting to see what happens when we put together two hell of Einstein telescope, 15 kilometers long, with the two Cosmic Explorer detectors, the two interferometers of Cosmic Explorer. And then you can see the numbers, and you can see the increase that we will have with respect to the second generation detectors that we have now. So it's a huge increase. So we are also considering the risk assessment, in particular connected to all the phases of integration, commissioning, science, and operation. We appointed a dedicated committee that prepared a metric, a risk metric that was applied to both configurations and prepared a detailed report that is under review currently of the executive board. So I cannot show you the results, but also here there are indications that having two hells instead of one triangle is probably less risky. So in practice, from these two committees, from these two studies, we are now considering currently two possible configurations: the triangle with 10 kilometers long arms and two hells with 15 kilometers long arms misaligned. That means one site in a case and two sites in the second case. But this evaluation is still under discussion because we have to consider all the concerned aspects that this choice will imply, and also to apply some mitigation strategies that can be applied indeed to reduce, for example, the risks in the two configurations. And this discussion is ongoing at higher level, at the level of the funding agencies, at the level of the government representatives. So yeah, what we expect is that in the next few years, we will have finally the decision of the baseline and also the site or the sites if there will be two hell. So the last part of my presentation is indeed about the sites that we are studying for ET. There is a site here, you can see at the border between Netherlands and Belgium and Germany, which is called the EMR. And then there is another site in Italy, in the Italian island of Sardinia, in the so-called Sosenatos area. If you look carefully here, there is also a black dot here. There is indeed a possible site in Germany, at the border with the Czech Republic and Poland, which is called the Lusatia. But this site is still not official, but however, we are studying, we are characterizing also this site. So the overall site evaluation obviously is a complex task. From our side as scientists, we are almost interested almost completely in the geophysical aspect, in the environmental noise, and so environmental quality, but it's just a part of the evaluation process because we have to take into account also the financial and organization aspects, and then also those connected to services infrastructures. And from what concerns the scientific part of the evaluation, we are in particular studying the seismic noise, the related Newtonian noise, the magnetic noise, and the acoustic noise, which are the main sources that we have in the low frequencies that can limit the sensitivity of our detectors. In particular, ET will be much more sensitive to environmental noises with respect to Virgo and LIGO. Currently, in particular, one of these sources of noise, which is important below 10 Hertz, the seismic noise that can be generated either by the geophysical activity of Earth, but also by the activities of the people around, all the what we call the anthropogenic noise. Okay, and for ET, the characterization of these sources of noise is crucial. It's crucial for the design. It's crucial also to define the noise mitigation, the active noise mitigation strategies that we have to apply and to define the control systems for the interferometers. So ET, as I said, will be an underground observatory. And for this reason, we are also interested in measuring noise underground. So for example, we excavated boreholes, we placed the seismometers, magnetometers inside these boreholes, and we are measuring the noise, in particular underground. The reference is 250 meters because we expect that the Einstein telescope on average will be at that depth. And I have to say that also both sides are strongly supported by the hosting nation. In the case of EMR, we have support by the government of Netherlands of about 900 million euro if the infrastructure will be built in the border region of Netherlands. And in Italy, we have also the support by the national government with 950 million euro plus 300 million that will be provided by the local government of the island of Sardinia. And currently, we are also at both sides starting a study from the geophysical point of view and the structural point of view, engineering point of view, of the ET infrastructure at the two sites. It's a preparatory study for the engineering design of the infrastructure. There is a contract started in Netherlands of about 2 million euro and another contract in Italy of about 12 million euro. Just to give you an idea of the low noise that we expect in ET, this is the seismic noise. This is the spectrum of the seismic noise. And these two panels above are measured in a borehole in Netherlands, in this place, Tertiet, while these two panels below are measured in Sardinia, in another borehole, which has the same depth, more or less, with the similar seismometer used for both. And we are interested in particular in this part of the spectrum, from few hertz to 20 hertz. And you can see that in Netherlands, we are measuring something around 10 to the minus 9 meters per second, while in Sardinia, we have in practice a factor 10 lower seismic noise, 10 to the minus 10. So this is the first indication. Here we can see the same, but here I included also this preliminary spectrum that we have from another borehole in Germany, in the third site that I mentioned before, that is still not officially candidate, but we are studying. And you can see that it's similar to what we have at EMR. So currently, the Sardinian site reached the lower seismic noise. This is true also for what concerns the magnetic noise. And one interesting thing is to project this seismic noise in terms of a gravitational noise that we call Newtonian noise, produced by the seismic waves, the compressional seismic waves, as a gravitational noise acting directly on the test mass, on the mirror of the interferometers. So if we use the seismic noise that we measure in Sardinia, here we projected the 10th percentile, the median, and the 19th percentile. In blue is for Sardinia, in red is for Netherlands, and we compare with the black line, which represents the sensitivity of ET. We can see that in Sardinia, indeed, we will expect to have the need to mitigate just a small amount of Newtonian noise, while in Tertiet we will require a stronger noise subtraction from the output signal of the interferometers. So in conclusion, ET will be a third-generation gravitational wave observatory, increasing the horizon, the observational horizon, back to the dark edges of the universe. So it will have a huge impact on multi-messenger astronomy, cosmology, and even fundamental physics in extreme conditions. ET will be the larger and more underground research infrastructure in the world. and also it requires to push greatly the technological improvement, all the enabling technologies that we need to build such detectors. It is in the European S3 roadmap. We have currently two baseline under study, that is the 10-kilometer arms triangle and the 15-kilometer double L. And the international collaboration is still growing and already counting more than 1,600 members. There are two sites that are officially candidate to host infrastructure. Both are strongly supported by the hosting nation, and there is an extensive site characterization activities ongoing at both sites. So this is my last slide. Thank you for your attention.
Thank you, Luca. So we have several minutes for questions or comments. Yes, 이영모 교수님.
So when you compare between triangle and two Ls,
Yeah.
and two Ls will be located at the same site, or they will be separated by?
Yeah, we started the study placing the two healths in the two candidate sites. So in Netherlands and Sardinia, we consider the distance between the two sites that is fixed by this geographical distance between Sardinia and Netherlands.
So one L is located in Netherlands and the other?
Exactly.
Okay.
광공 의원님.
Yeah, somewhat related question, but different. For the 3 detectors, why multiple detectors at the same location? What is the merit of having 2 or 3 detectors instead of single detectors?
You need more detectors to find the source location in the sky, because we want to have an observatory capable of giving the direction of the incoming waves.
Then we need some distance interval between detectors.
Yeah, if you are indeed you achieve a better localization if the 3 detectors are distant from each other. But if you use a triangular shape and you put together all the detectors, the 3 detectors there, in this case, since the gravitational waves has 2 polarization plus and orthogonal polarization cross, you are still able to make a localization even with a smaller distance, because you have collocated all the detectors. But obviously, the capability to localize the source is better if we have the two. Oh, sorry, if you have the two healths. Yeah, you can see clearly that the resolution is would be better. And yeah, this is one of the point of discussion. Also, obviously, if you had more detectors, in particular, we are considering to have also the 2 cosmic explorer detector. The situation improves greatly. For more detector, you have more precise you can be with the sky localization.
Any other question? I have one question. So ET for the low frequency region has many technical challenges, but why the low frequency observation is so important?
Yeah, low frequencies are important because at low frequencies below 10 Hertz, we expect to have, for example, many spinning neutron stars, isolated neutron stars that we can observe, integrating the signal, the observation along the time. We can also observe larger masses coalescing black holes. We can observe the first part of the coalescences before the merger. So we have a lot of astrophysical sources that are important coming from this part of the spectrum. So also if you observe a coalescing neutron star for a longer period, so you have your detector band with the signal for more time, you are also able to better localize the sources before the merger, before the arrival then of the optical counterpart signal. So it's a great improvement. And indeed, you can see in one of the first slides, maybe like this one. Here you can compare the situation with ET in green and Cosmic Explorer in purple. ET will be able to reach lower frequencies with respect to Cosmic Explorer. And you can see it, here you have the total source frame mass, and you can see that the green line is at a larger horizon with respect to Cosmic Explorer for higher masses. And these intermediate mass black holes are also of interest because, for example, as I said, it is interesting to see if how many of them we can localize, we can identify, and maybe review the population of this kind of object. Maybe we can understand that primordial objects of these masses are the seed for supermassive black holes. So we can learn a lot from this kind of sources.
Okay. Any other question? Okay, then I can ask another question. So ET already has more than 1,600 members, but
Yeah.
and do you think it will be enough, considering that the scale of the project and complexity of the detector in the future compared to the LIGO and Virgo collaborations?
Yeah, no, it's good to have such a large collaboration. Now we have probably to focus on building the detector. So we need manpower, let's say, working on the experimental part, on the hardware, on the design, and also on the R&D, on the technology that are required for ET. We have in front of us like 10 years. So in these 10 years, we have to enable all the technologies that are needed. And I think that the numbers are the right numbers for such a large project. Probably now we will be more selective with the new entries in the collaborations, but I think it's good to have it still growing, because it's clear that it's still attracting people, still attracting scientists, because as I show you, there is a lot of science that we can do with it. So it's a good thing, I think.
Okay, thank you. And any other question? Oh,
You show that the noise in low frequency range in Sardinia was much better, lower than the other area. Is it mostly that kind of noise level is produced by the human activities, or is it mostly other geoseismic?
Yeah, let's say that still few hertz is mostly produced by geophysical activity of Earth. Above a few hertz, above 2 hertz, above 3 hertz is mostly produced by human activity. And in Sardinia, what we have is that the geological setup is completely different from Italy. Italy is like Japan, is very active place with many fault lines that are active. Sardinia is completely different. It's another continental plate. It's a microplate with the island of Corsica, which is one of the most ancient parts of Europe, actually, and is fixed in its position till tens of millions of years. And for this reason, it is very stable. Also, the underground rocks are very good because there are granitides which are also good geomechanical properties to excavate such large underground infrastructure. There are no active fault lines. So for this reason, this is seismically very, very stable. Indeed, for our measurements, what we found is that I go back to the spectrum, between 4 and 7 hertz, so more or less here, we have one of the lowest seismic background noise in the world. We compared with the international network of seismometers. The seismic stations that we built in Sardinia are the most quiet in the world. It was really interesting also for our geophysics colleagues looking into this data. They in the past, they were not interested in Sardinia because Sardinia has not earthquakes, not activity, so they didn't care about Sardinia. Now that we are demonstrating how quiet it is, they are greatly interested because in placing a seismic station in Sardinia, they are able to study the, for example, oscillation of the Earth nucleus, to be sensitive to far low magnitude earthquakes. It's a really peculiar situation also for them. So there is an increasing interest in the project, even in the project by the geophysical community, because from our error signal, they can do science for what concerns geophysics. And in Sardinia, we have also another peculiarity, that is a very, very low population density, which is one of the lowest in Europe. And also for this reason, we have above 2 Hertz, still a very low noise background. By contrast, in Netherlands, we have some fault lines and we have a lot of population around because there are big cities like Maastricht, Aachen, and Liège that are close to the site. There are pros and cons, I mean, because Sardinia is underdeveloped from the infrastructure point of view, while Netherlands and Belgium, we have a lot of infrastructure, airports and so on. So the evaluation is always a trade-off between the scientific needs, and clearly Sardinia is much better from the scientific point of view of the noise, but also the needs of such a large infrastructure, research infrastructure will have in terms of services, accessibility and so on. So yeah, it's a difficult evaluation, but from what concerns the scientific data, the noise data, what we see is that Sardinia is probably the best place. But let's say that in the case of having only one observatory in a triangular shape. Personally, I think that at this point, since I already showed you that the results of the evaluation committees, the 2 Healths are probably the best choice. So in this case, we will have one in Netherlands and Belgium and one in Sardinia.
Okay, so time is up already. So, but if you have any more question, we will have a special session for gravitational wave in the afternoon. So please join. Okay, let's thank our speaker again. Thank you.